So this was a pop quiz related to standing waves, Unit 2. And this was a pop quiz 2. Photograph shows a musical instrument which is also known as a violin. It has four strings, each is held at a fixed position by a peg, as you can see, and fixed by the pegs, and the bridge is there at the bridge. When a string pluck, a stationary wave or a standing wave form. Explain how standing wave form. This is a very common question. Almost every year you will find this. So you have how standing wave is produced when two progressive wave traveling in opposite direction and they interfere with each other, and the resultant wave is the algebraic sum of the two. That is called a standing wave. So two progressive wave moving in opposite direction combine or interfere with each other or superimpose and give rise to a standing wave which result in a formation of nodes and antinodes. Where they increase the effect of each other, we get antinodes, and where they cancel out the effect of each other, we got nodes. So explanation here, two progressive waves traveling in opposite directions. Superimpose or interfere they will give rise to a standing wave with nodes and antinodes. Nodes are the region where they increase the effect, antinodes are the region where they cancel out the effect. A simplest stationary wave that can be formed in a string, nodes and antinodes are there. The frequency of this is called a fundamental frequency. The string of a violin have a different fundamental frequencies. As you can see, the first string is having a fundamental frequency 196, then 294, 440, and 659. The tension in one of the string is 71.5 newtons, and the length of a string is 32 centimeter. The mass per unit length, or you can also consider the thickness, is 2.03 exponent minus 3. Deduce whether this is a string 1, 2, or 3, or 4. So first what we will find, we will find the speed. Look, speed, there are two formulas for the speed. Speed is frequency multiplied by wavelength, or speed is under root t divided by mu. That is the speed. The two formula, this is a wave formula which is applicable for all kind of wave, and this is a formula which is only applicable for the string instrument. Now, first we will use this formula. V is under root, because we have the mass per, we have the tension, the force and mass per unit length. First we'll find V. We'll get the V, and then when it is vibrating in one loop, what about the wavelength? The distance between the two successive nodes, that is given by lambda by 2. It's a half of wavelength. So we can say length is equals to half of wavelength. So lambda will be equals to 2L. So lambda will be equals to 2L. So V over 2L will be equals to F. So after getting F, and the length of a string is also given to us, which is 32 centimeters. So we'll substitute. So first we'll find the speed at which this wave will travel, which is under root t divided by mu. So t is 71.5. And mu is the mass per unit length, which is 2.03 to 10 power minus 3. This will give us the value for V. What's the answer for V? 187.7 meter per second. Now, after getting V, 187.7 divided by 2 multiplied by length. What about the length of a string? It is given 32. We have to convert into meter, divide by 100 to 0.32. So this will give us a frequency 293. So 293.3 hertz. So 293.3 hertz, it matches with which? So this matches with string 2. So means this is string 2. So we work out the fundamental frequency, and from that we concluded which string was there. Then in part C, the stationary wave on a string causes the sound waves to be transmitted through air. Describe the similarities and difference between a stationary wave on the string and the sound wave transmitted. Look, what actually happened is these are the string instrument, and when it causes a vibration to air particles, like if this was a surface of a violin and a string is vibrating, it cause a vibration to air particles. So air particles hit and bounce back, and these like the two progressive waves moving in opposite direction. This will give rise to a standing wave. But this is a standing wave of a sound, and here it will be a standing wave of a string. What we have to do, we have to write the similarities between them. Similarities and the differences, and it's a 5-mark question. So first, what will be the similarity? Because the speed at which the frequency at which the string is vibrating is same as the frequency at which the air particles will vibrate. Like if the string is having a frequency of say 294, the air particle will also vibrate with the same frequency. So they will have the same frequencies, the air, same frequency for a string and air particles. And what will be different? The speed will be different. Because different speed for a string, because two different mediums are there, so the speed of a wave will be different. It depends on the medium. Another thing, as a result, what will happen? The sound waves, when they are produced, it's not like because in a standing wave, what happened? That the amplitude of a vibration is changing. It's not same throughout. Like here, amplitude, this is amplitude, this is a maximum amplitude, and that is called antinode. But the amplitude for a string will change. Amplitude for the string will change, but what will happen for the amplitude? Amplitude for the sound will be constant. It changes when it progresses from one place to another, but in that region, the amplitude of a sound waves, that will be constant at that region, that specific place. And standing wave does not, whenever standing wave is there, it does not transfer energy. But the sound waves, as it travels from one point to another, it will transfer energy. So these are the points you can refer. Which of the, it's not like this, we are talking about the standing wave produce sound wave. It is what happens when these strings are vibrating, they cause a vibration to transfer. So we are comparing the waves in the string, and we are comparing the sound wave. So sound transfer energy, string does not transfer energy, it's a standing wave. Sound, the amplitude is constant for that region, but string, the amplitude is variable. For sound, transfer energy, the string does not transfer energy. And the speed at which the wave travel in sound, waves travel, that is different compared to wave in a string. Then which of the following is not a correct statement about the stationary wave? All points between the adjacent nodes are in phase. What does it mean? Like example, if this is a stationary wave or a standing wave, all points in the adjacent nodes, like this is one node and this is another node, are in phase, like they're vibrating in the same manner. Yeah, that is right. Like if these particles are moving, so they so all points between the two adjacent nodes are in phase. So that between the adjacent node, these all particles are moving in the same manner. That is correct. Antinodes are the point of maximum amplitude. That's also correct. Antinode is a point of maximum amplitude. Distance between the adjacent node is equals to one wavelength. The distance between the two adjacent nodes is half wavelength, not one wavelength. So this is not correct. The net energy transfer is zero. The stationary wave does not transfer energy. So this statement is also correct. So C is the right answer. So stationary wave does not transfer energy. It just produced by the two progressive waves traveling in opposite direction. So this was a pop quiz related to standing wave.